you, viewers. This is Mr. Ringo again, coming with a new sub-chapter that is sum to infinity of geometric progressions. Now, infinity means something that is unbound, something that continues until an unknown limit. We are not binding it to certain boundaries, maybe between this number to this number. For example, in the previous lesson, when we talk about geometric progression, we were telling you to get the sum of 10 terms. So when you get sum of 10 terms, already you are bound your limits between 0 to 10, the first term to the 10th term. Now, or 20 terms, or 50 terms, or 1,000 terms, or 1,000,000 terms. That is still meaning that you have actually given your term to a certain boundaries or limits. But when I say sum to infinity, infinity, this is the symbol for infinity, meaning that the number of terms n here are not actually known. We know that we do sum of n terms, but in this case, the finite values, when we actually put some boundaries between unknown values of n. In this case, sum of infinity, we actually do not know or cannot tell where the value of n is. So it continues and it continues until God knows where. Now, when we now come to a sum of infinity of geometric progressions, what we can tell is that we have two types of, in a geometric series, we can calculate sum of terms in a geometric sequence. However, as n tends to infinity, meaning n goes to an unknown number of terms, the sum of the series is called sum to infinity, which is given as this is symbol for infinity. Now, there are two types of series here. We have the divergent geometric series and the convergent geometric series. Now, a divergent series whose sum will always spread from maybe smaller figure and goes to a much bigger figure that we cannot actually determine. Sometimes if you have to express that in a calculator, you will not get an answer because it's something that cannot actually be expressed. It's so big. And that's why we say that if we have to get a divergent geometric series, that the number becomes bigger, the sum becomes bigger or becomes infinity. Let me say infinity when n tends to infinity. N becomes a number that is so big that we can actually determine. So the sum of that number becomes as well very big. That's why we say that in a divergent geometric series, as n tends to infinity, so does the sum. The sum also tends to infinity. For example, if I have the sum 2, 4, 8, 16, 32, 64, you realize that in this case here, r is more than 1. It's 2, 3. It means that the number keeps on building, becoming bigger and bigger and bigger. So as you continue adding the value of n, this is n1, 2, 3, 4, 5, 6, n7 will be something bigger, n8 will be much bigger, n1,000,000 will be much more bigger, billion will be the value of the sum of the geometric series of the sum actually will be much more bigger than a calculator or anybody can write down. So that's what we refer to a divergent geometric series. It occurs when as n tends to infinity, the sum also tends to infinity because increase in n will also increase the sum of those number of terms. But when you come to convergent geometric series, you realize that as n tends to infinity, as we give the many number of n in a certain particular geometric series, the sum approaches a finite value. And I want to show you something here, that if I have 1, this is a series, plus a half, the one we have here, plus a quarter, plus 1 over 8, plus 1 over 16, plus 1 over 32, plus 1 over 64, plus 1 over 128. Let's see in a calculator what we are going to have. So you realize that as the number of n, this is n1, this is n1, 2, 3, 4, 5, 6, 7, 8. This is n8. It means as n becomes bigger, maybe 9th, 10th, and 100th value, a millionth value, what is going to be happening to the sum? So you realize that as this value becomes smaller, this is 1 plus 0.5 plus 0.25 plus 1 divided by 8 is going to be 0.125 plus 1 over 16. 1 divided by 16 is actually 0 0.0625 plus 1 over 32. 1 divided by 32 is 0.03125 plus 1 divided by 64 is going to be 0.0152625 plus 1 divided by 128 is 0.0782125. Now you realize that if I start adding these figures, 1 plus 0.5, 0.5 will have some significant change on this one. 0.25 will also have some significant change on the sum. 0.125 will have significant change on the sum. When I reach here, you realize that this decimal point here, this one will not be affected by this because the next decimal point here is 0. So when I start reaching here, the change on this one, on the sum, will be much more less significant. When I come here, much more less significant. When I come here, even much less. When I reach here, 1 over 128 here, the change on the sum will be much more less significant. It means that even if I add this, the changes on the first two decimal places on the sum from here, the sum of this one going upwards, on the first two decimal places will be much more less significant. It means that as the number becomes, as n becomes bigger, the sum becomes more real. The sum becomes more real or much more constant as you add those much more 0.0 something. So that's why I'm saying that when it comes to convergent geometric series, as the value of n approaches infinity, the sum of this geometric series approaches a much more constant value. And if you have done Pascal's triangle, or what we call a binomial expansion, you can be able to understand this. That's why sometimes you are told to use a given number of terms, maybe the fourth term, to estimate the sum of the first 4 terms. And you realize that why do they tell you to use the first 4 terms? Because if you go up to maybe the 10th term may have almost 0 effect, or very minimum effect or minimal effect on the actual sum of the first 4 terms. So that's actually what we are talking about here, that as the n becomes bigger, the answers that you have, because this thing keep on decreasing. Can you imagine if you have maybe, if this 8th term, if you have the 16th term, you expect that it will be something probably 0.0000, maybe up to maybe 6 zeros for you to have actually a significant number. So that's what we are trying to explain here, that as the value n becomes bigger, the actual answer, the value of that term becomes very small. So the value of the total sum of the terms that are involved there will approach some kind of a finite value. And that's what we have here. So we say that a geometric series is said to be convergent if and only if, and in mathematics we have if with the double F. That means if and only if absolute R. Absolute R here means that it could be either positive or negative. So absolute R could be -1 or +1. It means that if it is, we are talking about absolute R, meaning we have got, I can have positive, negative here, which is this R, which is this 1. So it means that the value of R can be greater than -1, but must be less than 1. Anything other than that must not be considered to be a convergent geometric series. So the ratio must always be something 0 point, -0 point, +0 point. We cannot have something more than that. If I have -2 or if I have +2, that value there will not be accepted as convergent value. So that's how you are going to test for this particular series to determine whether something is convergent or actually divergent. Now I want to bring you to the workable results. We know we have got the formula for getting the sum of n terms when r is less than 1. The sum of n terms, we have said, is a into 1 minus r power n over 1 minus r. In this case, we have said this one is where r is less than 1. So we realize that if that's what we are going to talk about in this particular case here, we have absolute value of r. And I've said as absolute value, meaning that this one can be positive or it can be negative. So if we say in a case where, we have a case where n n what? Tends to infinity. N tends to infinity, where n tends to infinity. What happens? N approaches infinity. What do you expect R to be? R will always be also approaching 0. That's what you expect to see. As you keep on moving that particular direction, you expect these values of R to approach 0 as n tends to infinity. So if this R actually approaches to 0 and becomes 0, it means that n power 0 will just be 0. And so we are going to have 1 minus 0 is 1 times A. The formula for sum of sum to infinity of these terms here will therefore be A, because we have said when this one approaches, when R approaches 0, when R becomes too small, that is also very close to 0, then this one becomes 0. So 1 minus 0 is 1, then times A is A divided by 1 minus that R. So this is going to be the formula for our sum to infinity of the convergent geometric progression. As you notice that we cannot be able to get the sum to infinity of divergent geometric series. Why? Because we have said that as n tends to infinity, the sum of n terms also tends to infinity. So there's nothing that we can actually generate there. It means the numbers keep on becoming bigger that we can actually not calculate. But when it comes to convergent values here, we have said that we can actually see what is happening. As R approaches 0, because n is tending to infinity, then what is happening here? What is happening here is that this one becomes 0, and when this one becomes 0, we have sum to infinity, and R is 0 here. When R is 0, 1 minus 0 is 1 times A. We have A, and that's the formula we're going to use to get the sum to infinity of convergent geometric series. So in terms of sum to infinity, we are not going to talk about divergent anymore. We are going to just take it because that's what we have the formula to be able to calculate. In this case here, n is our limit. When n actually becomes 0 or n becomes infinite, R becomes 0. That one, we have a formula, and we have said this formula here. Note that it can only be used for what? For convergent geometric series. Convergent geometric series only is convergent. Show that this series is convergent. We said that a convergent series R should almost be less than 1. We said that for convergent series, absolute R must always be this. So if you get R to be either negative value, that is 0 point something, or a positive 0 point something, then that can tell us that that particular series is convergent. So here we know that the fourth term of a series, we know that A, the nth term, Sn of a series is A R n minus 1. That's what we know for series. So if the fourth term here, Sn is 4, the fourth term is 1.08 equals to A, we don't know A, R here, we also don't know R power 4 minus 1. So that will be 1.08 equals to AR3. What about, this is the fourth term. What about the seventh term? The seventh term is actually 0.02328 to be equal to AR power 7 minus 1. That will give us 0.02328 equals to AR power 6. Now from these two equations, equation 2 and equation 1, we can be able to do something. We can be able to get A from here, or A minus to R. So if I have this one, what we are going to do here is that if I take this equation, that is AR6 divided by AR3, I should get 0.02328 divided by 1.08 8. From here, A and A will go, and then R power R, I'll get R power 3, because R is the same as 3 minus that, will be, if I divide that, I'll get 0.02328 divided by 1.08, get 0.0215555 recurring. We just have 5 6 times. So if I want R equals cube root of answer, which is 0.2783, correct to 4SF. Part B of the question is find the sum to infinity. So viewers, before I go to that part, I want to be able to explain something. We were told to show that this series is convergent. And I said that for us to show that, the only thing we have to show a convergent series, we say that absolute R should be less than 1. And actually we have seen that R here is less than 1 because R is 0.2783. So we have indicated, we have really proved that this is a convergent series. So we know that sum to infinity, sum for infinity is given by the formula A over 1 minus R. So if 1 minus R, what we are going to do here, sum to infinity in this case is going to be A, the first term. The first term we have not calculated, but now we can get it because we have the formula here. We have our R, we bring R here, so we are going to say if let us get A. So if I have this, we know that using the first equation, 1, let me say AR power 3 equals to 1.08. That's our equation. So if you want to get, we know that A here will be 1.08 divided by R power 3. So A will be, and we know that R power 3 is here. This is our R power 3, so I'll simply say 1.08 divided by, let me see, that is going to be 0.0215555. So A is going to be, let us see, 0.0215555. So 1.08 divided by answer is going to be 50.1, correct to 3 significant figures. 3 significant figures. That's what we have. So if that is our A, then I'll say A is 50.1. And I've said there are many decimals, but I've expressed my answer correct to 3 significant figures. Over 1 minus R, and our R is 0.2783, again correct to 4 significant figures. So this will be 50.1 divided by 1 minus 0.2783. That is giving me 69.419, correct to 3 DPs, 3 decimal places. So that is going to be my my sum if A is 50.1. We just have to come here to get that. So the second example here says that for a geometric series with the first term A and a common ratio R, the sum of the first 4 terms is equals 15, and the sum to infinity is 16. Find the possible values of R. So what we are going to do here is that we are going to use the formula for the sum. We know the sum of n terms is normally given to be A into 1 minus R power n over 1 minus r. Remember this formula we are going to use for this, because this one is actually a sum of an finite value, sum of 4 terms, but this one is sum to infinity, meaning unknown. So this one we are going to use for the question 2. So I'll say that the sum of this one 15 equals to a into 1 minus r power n over a over r over 1 minus r. So this one here is something we are going to see. We know that our n here is 4. Yeah, so we are going to substitute 4 where 4 is. So we are going to see r power 4. We cannot do something about that. So we leave this one as our equation 1. But we know we can also go for equation 2. Let me continue here. For sum of infinity there, you know sum of infinity is given by a divided by 1 minus r. So sum of infinity is 16. 16 here equals to a over 1 minus r. That is equation 2. So can we be able to deal with something here? We know that if I multiply this by this, 1 minus r and a, yes. So if we multiply, let me say we cross multiply here, we are going to get 16 1 minus r equals to a. This is, let me say this equation 3. But for the first equation we can also say 15 into 1 minus r equals to a into 1 minus r power 4. So again, in this case, we can be able to express this in terms of a by dividing both sides by 1 minus r power 4. Here, 1 minus r power 4. So this and this will go. So we'll say a in this equation will be 15 into 1 minus r over 1 minus r power 4. This is equation 4. So we realize that this equation 2 and equation 4, we can be able to, not equation 4 but equation 3 here. We can be able to say that this one now equals to this, because this is a and this is also a. So I can say 15 1 minus r over 1 minus r power 4 equals 16 into 1 minus r. Now from here we have to be able to do something. If I divide, no, let me not go there. Yeah, so if I have here 15 into 1 minus r equals to 16 into 1 minus r power 4 into 1 minus r. So divide by 1 minus r, 1 minus r, 1 minus r, 1 minus r will go. So here we are going to have 15, or let me start from here, 16 into 1 minus r power 4 equals 15. So if I have 1 minus r power 4 is actually 15 over 16. So 1 minus r power 4 equals 16. 15 divided by 16 is actually 15 over 16. So let me take 1 the other side. So I'll say negative r over 4 equals to 15 over 16 minus 1. Negative r power 4 will be minus 1 is negative 1 over 16. So negative 1 over 16, we know that negative and negative will go. So r power 4 equals to 1 over 16. So we get the fourth root of this part, fourth root, and the fourth root. But we know that this is an even number. So if an even number, the fourth root will be either positive or negative. So we can say r here is the fourth root, 1 divided by 16. So shift, now 4, shift, fourth root of answer is a half. So it will be plus or minus a half. So we know that in this case r is either plus or minus. The reason why I'm bringing plus or minus here is that this is an even number. If it was an odd number, maybe power 5 or power 3, answer can only be 1. But in this case, it's an even number. So the square root of any even number will be either negative or positive. Now, we say that the positive values of r can be positive a half or r can be negative a half. That's the equation that we were expected to get. Let's go to part B. Find the value of a. So we know that if the values are all positive, then it means r is positive. That's what we have to conclude there. So we know r therefore must be positive a half if all values of the series are positive. So if you are getting the value of a, let us get the sum of infinity, which we said the sum of infinity was 16, but we know the formula for sum of infinity is a over 1 minus r. So we can actually say, if this is the point that we have here, then what is our sum to infinity? 16. So we can say 16 equals to a over 1 minus r, and our r we have said must be positive a half. So we are going to say a will be, this is a half, so 16 times a half, which means a is 8 if we are dealing with that problem that we have there. So viewers, this is the answer that we are supposed to give, and really that question requires you to at least think and be able to deal with a lot of algebraic expressions. So really some of these chapters, if you are not good at a particular chapter, the other chapter will also not be good with you. So you have just to try to ensure that you master various chapters that are very important. Particularly algebra is very key in different areas. Algebra, logarithms, indices, and so on. Thank you, viewers.